All right, so our objective once again is I can simplify algebraic expressions, the big idea or the big concept of algebraic expressions. And what are we doing? We're simplifying. All right? So, from there, let me get my PowerPoint in front of me. Okay. All right, so at this point, writing utensils down, look up to the screen, please. So, it's imperative that as I ask you to stay focused, because I'm going to start reviewing some concepts that you should know by now, and I'm going to clarify stuff that maybe are getting you confused with some of the math that you've been looking at. First thing is expressions. Expressions. One thing we cannot do with expressions, here it goes. One thing we cannot do is we cannot solve expressions. So, if you've encountered in the past when you were in your other math classes and somebody said, or in a quiz, they told you, simplify this expression, all of a sudden you ended up with x equals something, or you just solved it. You cannot solve an expression. You can only simplify expressions. Therefore, we cannot solve. What can we do? We can do three things. The first one is we can translate. The second one we can evaluate. And the last one that we use the most is simplify. Okay, once again, you're just paying attention. I'm just showing you I'm going really quick to run down as to what these are. To translate, that means I need to have a specific expression. Here's an expression. A number plus 23. This is an expression. Can I translate that into symbols? Yes. So I start with the first part. All right. So look up, please. It says a number. Do we know the number? No. So what does that mean? That we need to replace that word with what? Some of you right away said x, but not necessarily. We can use any variable, yes? So I'm going to use the variable q. What's the next part? Plus. And the last part? 23. There it is. We just translated an expression. Is it coming back? Remember? Back in the day? Okay. Next. To evaluate, well, somebody needs to give us an expression and they need to give us a value for the variable. So let me give you a value for the variable. Let's say that q is 100. So now that we have the expression to evaluate, we need to take this value and substitute it in there. So what is it going to read now? 100 plus 23. The last step, check this out. The last step here is what we call simplify. So what did we just do? We did three things. We translated, evaluated, and simplified. Now, is that the only way that we simplify? No, I'm going to give you these long expressions where you're going to have to crunch stuff to make it smaller. Did we solve anything? No, we made it smaller. Are we clear on that? All right? So, those are expressions. Next, I'm going to take you back to when you guys were babies. When we started our life, we started with real numbers. And real numbers are numbers that we can use every day, that we can actually do transactions with. Like when you go purchase stuff, you give a $5 bill, you get change back. Those are real numbers. Okay? Now, real numbers are broken into two sections. Here they go. The first section is rational numbers, and the second one, irrational. But all of them are still what? Real numbers. Are we there so far? Is it coming back a little bit? Yeah? Rational numbers, there's counting numbers in there. You guys remember? You were in kinder. I'll race you on the swings. 1. There they are. Those are the counting numbers. From there, the other ones are whole numbers. Whole numbers are the counting numbers, but including 0. Here it is. Yes? The last ones of the rational numbers are integers. Integers are whole numbers, but including their opposites or the negatives. There they are. You're like, oh snap, it's coming back. Yeah, yeah, the integers are never going to leave. All right? So I'm just clarifying here. So now, all of these, once again, they're rationals, and all the rationals and irrationals are real numbers. Okay? Are we clear up to right there? Now check this out. I'm still focusing on rational numbers. Focus, please. Here's the definition for rational numbers. All of these. All of these are rational numbers. A rational number can be made into a fraction. Tell your neighbor what I just said. Okay. So for example, Jordan, how can we make 3 into a fraction? 3 over 1. There's the fraction right there. What if I gave, let's see, Wow, if I gave her 1.25, what is 0.25 in fraction form? 1/4. I'm going to bring this down, the 1. So I'm going to see if I can make this into a fraction. Is this a fraction? No, it's a mixed number. Can I make that into a fraction? What is 4 times 1? Plus 1. So this is 5/4. So that means this is a rational number. Any number that can be made into a fraction is a rational. Any number that can be made into a fraction is a... So if that's the definition for rationals, think about it. What is the definition for irrationals? Things that cannot be made into a fraction. Isn't it obvious? Yes? All right, so let me show you the ones that cannot be made. So here we have, you can barely tell there, we have pi. You guys remember pi? 3.14, and it keeps going. It never stops. There's a supercomputer that they typed in the formula for pi, and it's still going. Yeah, it doesn't end. Next, square root of 2. Square root of 2 comes from the square. If this side measures 1, this side measures 1, the area is 1. But if I wanted to know this distance right here, I would have to use the Pythagorean theorem, and that's how they get square root of 2. That's a never-ending number. Another never-ending number is this one, 5. You're saying, what? 5, I introduced this to some of you in Frank Wright, and this one is 1.618 ... and it keeps going. Now let me take a little pause here so I can enlighten you. Here we go. Ready? Pi is something that we have in our DNA. You're saying, what do you mean, Mr. Q? If I asked you to go home today and measure your height in inches, got it? Divide that by your distance from the top of your head to your belly button. Guess what number is going to come close to? By 1.618. You're like, no way. Yes. What if I told you that if I measure your arm from the shoulder to the tip of your fingers and divided it from your elbow to the tip of the fingers, guess what number is going to give me? 1.618. Or, let me put it in your terms. What if I asked you to get your cell phone at home? You're like, what? Yeah, measure the long side by the small side. You're like, what? Okay, let me continue. What if I asked you to go into your pantry, get a cereal box, measure the long side divided by the small side, 1.618. Wait, what if I asked you to get your ID out? Divide the long side by the small side. What if I asked you to measure the iPad, the long side by the small side, and that gives us close to 1.618. This is what we call the golden ratio. And since companies know that that's still in our DNA, they use that to sell us stuff. That's why everything from the smartwatches to the cell phones to the tablets, they all are in rectangular form, most of them. And they all use which ratio? Exactly, because we go towards that. Go figure, huh? You're like, what? I know, right? Anyway, so that's enough of that. And the last one that doesn't end is E. That one is 2 point yada, yada, yada. That's the Euler number. And once again, all of those numbers cannot be made into a fraction. That's why these are called what? Irrational. These can, but all of them together are called what? Real numbers. Are we there so far? Now that we're starting Algebra 2, though, we're no longer just using real numbers. Now we're going to be using numbers that we cannot really picture. We have to use our what? Imagination. So what do you think those numbers are called? That is correct. Imaginary numbers. That's going to be the next segment that we're going to move into Algebra 2. Does that make sense so far? So we got real numbers covered. Now check this out. Here goes imaginary. Ready? Square root of negative 16. Pay attention to this part. If I said that square root of 16 is a real number because what number times itself gives us 16? 4. So that means this is a real number. So the rule is a number times itself to give us that number. So think about it. Talk it over to your neighbor. Let them know what number times itself gives us negative 16. What number times itself gives us that number? All right, everyone, what can we conclude? There is none. That's why we need to use our imagination to start using these numbers. That's why these are known as imaginary. Now, let me show you how mathematicians manipulated these numbers to make them in a way that we can use them. So here goes some Algebra 2. Ready? Writing utensils down, look up to the screen. I'm going to rewrite this first. Square root of negative 16 is the same as negative 1 times positive 16. Do you agree with that? Yeah, this gives us this. Okay. Well, now that we did that, now I can actually do this square root first. What is square root of 16? 4. What does that leave us with? Square root of negative 1. Well, this is called I. Therefore, this is 4I. You're like, what? Yeah. All we have to do, check this out. Some of you, this is where some of you get stuck. You're like, how does that happen, Mr. Q? Just from now on, anytime that you see a square root of negative 1, we're automatically going to change that to what? I. So let's see how that works. Ready? Here goes. Square root of negative 25. Look at it. Very similar to this one. So you need to read the imaginary number for that. 5I. Do another one. Square root of negative 64. Tell your neighbor the imaginary number on that. 8I. Everybody follow so far? Do another one. Square root of negative 100. Tell your neighbor that number. 10I. And so on and so forth. Everybody got it? So what are those called? Imaginary numbers. Are we there? So check this out. So now that we have real numbers, and what do we need to remember about imaginary? That I is the same as square root of negative 1. Are we there? So this is where it gets a little bit complicated. Some of you that maybe took this course before got stumbled with the next part. The next part, we're going to combine real numbers with imaginary numbers. And that new number is called complex numbers. Once again, what are we combining? Real numbers with imaginary. Let's see. Let's try and make one. Let's see. Give me a number. Anyone? Let's go. 23 plus. I need an imaginary number. 1I. 1I. Guess what? We just made a complex number. Everybody follow so far? Okay. So that's where we're heading once we get started with Algebra 2. I just wanted to connect the dots as to where we're at. So far, so good? All right. What's that? All right. Next, here's a flashback. Ready? Additive inverse property. Here it goes. Don't say anything. I'm going to show you the property, and then you're going to tell your neighbor the definition. All right, share with your neighbor the definition, please. Let's see, flashback. Let's start with Jacob. A number and its opposite is 0. What do we call these, everyone? If they're in pairs, they're called 0 pairs because both of them make a 0. So far, so good? Second property, identity property of addition. Here it goes again. All right, tell your neighbor the definition, please. All right, Omari. Any number plus 0 equals itself or equals a number. All right, so we're done with properties. Now we're going to get started. Just to clarify, numerical expressions are these: a number or an expression that uses numbers and operations. Oh, sorry. All of these are numerical expressions because all they use is numbers and operations. The other type of expression is, which one are we looking at today? Algebraic expressions. What did you guys notice on numericals that we didn't use? Variables. Well, guess what we're going to use for algebraic? Variables. What else? Numbers, and what else? Operations. Those three. So here we go. Let's fill out our prayer model. Ready? Algebraic expressions. Write this down, please. Algebraic expressions are expressions that contain variables, numbers or constants, and operations. Algebraic expressions are expressions that contain variables, constants, and operations. Examples: x plus 3, m minus 7, 2 times y, k divided by 5. And non-examples: x plus 3 equals 10, y equals 3x minus 2, 2 times y greater than 12, and 2x greater than y minus 3. Copy that, and I'll go over those examples. So, definition: expressions that use variables, numbers, and operation. Let's see, look at this one. Does it have a variable, number, and operation? This one? Yes, and yes. All of these have all those three components. Look at these. Tell your neighbor why these are not algebraic expressions. Yeah? We got this? Xavier, why are these not? Because they're equations. That is correct. And we're not in equations yet. We're in expressions. And the other ones are what? Inequalities. Are we there? So if I was to ask you to get your mobiles out and take a picture of this and send it out or snap it or whatever, what hashtag would you attach to this picture of algebraic expressions? Hashtag no equal sign. That's a good one. Karina? I don't have any. Hashtag wow. Hashtag variable. One more. Hashtag what? Constants. And so on and so forth. Yeah? All right, now that we're done with what expressions or algebraic expressions are, let's start with some work, yeah? Underneath your player model, you have some lines blank, is that correct? I want you to write example Q. We're going to start slow so I don't freak you guys out, and then slowly start snowballing it to what's next. Here we go. I want you to write simplify. Y'all ready? Here we go. Negative 2 plus 2. What is it? 0. Okay. How about 8 plus negative 8? 0. All these are what? 0 pairs. One last one. Here we go. How about negative 23 plus 23? And that gives us. So what I'm doing right now with these three, I'm getting your brain ready. Ready? Here we go. Next. 4 plus negative 3. Don't say it out loud. Everyone? 1 is correct. Now, for those of you that are still struggling with these, here we go. I want you to start thinking 0 pairs from this point forward. So, if that's true, are these 0 pairs? No. This is the smallest one. Can 3 of these cancel 3 of these? Yes. 3 negatives. Focus, please. 3 negatives cancel 3 positives, and that leaves us with what? 1. That's how we get that. Everybody see that? Let's do another one. Negative 7 plus 5. Don't say it out loud. Tell your neighbor, please. Negative 2. And once again, which one looks the smallest? The 5. Can 5 of these cancel 5 of these? Yes, and that leaves us with what? Negative 2. Are we there so far? Okay, here we go. Negative 50 plus 80. Everyone? 30. Okay, we got this, yes? So you notice how we're doing 0 pairs as we go along? Okay, let's crank it up a notch, yeah? Here we go. Example, mega Q. Moves out of the way. All right. Here we go. Negative 1 plus 4 plus negative 9. Let's copy it. Write your utensils down really quick. Now, there's 2 ways of going about this. You can go one number at a time, getting by pairs, but this is what I want you to start training your noodle to do. Look up, please. Start with the first term and check to see if there's other terms that look alike. Is there another term that looks like that? Yes, a negative 9. So what is negative 1 and negative 9? Negative 10 plus 4. Can 4 of these cancel 4 of these? Yes, and that leaves us with negative 6. Hands if you got that? Yeah, we got this, yeah? All right. Wow. Log out, please. And, yeah, pick who's going to put them away, please. Make sure they connect them. Oh, it can't be the same one as yesterday, by the way. So your home plate for tonight. Hopefully, make sure you get a packet, get it signed. Signed. Syllabus. Have a good one, guys. Enjoy your home plate. See you guys tomorrow. Bye.